This video is kind of a brief primer on what the determinant of a matrix is and also how to find the determinant of specifically a 2 by 2 matrix. So let's go ahead and get started by defining what we mean by a determinant. We say that every square matrix, and this is really important, has a number associated with it. So we say it's a special value. As a matter of fact, I want to make sure we make a note here. It's a scalar. A scalar is a real number that we can say multiply by or do something with. But essentially, every square matrix has a scalar value that is associated with it, and it's called its determinant. And we will explore many different properties of this determinant, but it is spelled thusly, okay? So what we're going to do in this video is essentially approach how to find the determinant of a 2 by 2 matrix, how we write it, how we interpret it, what we do with it, and then what we'll do is we'll look at, say, 3 by 3s in the next video, okay? So let's go ahead and start with this. We say the determinant of the 2 by 2 matrix specifically. So let's make a note here. This is very specific to 2 by 2s only. This method will not work with a 3 by 3 or any square matrix of higher order than a 2 by 2. So we say the determinant of the matrix A. Now we're going to say A, usually populated by a bunch of lowercase a's. What I've done in this case is I've defined A as being A1, B1, A2, B2, and I hope nobody minds here. But we say it's given by this matrix here. The determinant of the matrix A is given by this here. So we can write the determinant. First of all, how does one write the determinant of a matrix A? One thing you could do is you could just write det of the capital letter A. So that would be the equivalent here of me going back up to this equation here and saying determinant of this would be the same thing as the determinant of this matrix here. So another way to write it is just to say the determinant of the entire matrix would be the same thing as det of A. Okay. So you don't see that notation as often as you will see this. Now there's a difference between matrix A, which is this thing right here, and determinant of A, which looks very clearly like absolute value bars. So they are not absolute value bars, but we certainly write them that way. So if I wanted to write the determinant of this matrix A, another acceptable way to write this is indeed this way right here. So we could say if this is matrix A right here, then this is the determinant of A right here. This is the same thing as the determinant of A. So using these values in here, in general we say A1, B1, A2, B2, we say the determinant is A1 times B2 minus A2 times B1, which essentially, I could say B2 times A1 minus B1, A2. It doesn't matter what order you multiply in, but it certainly matters what order you subtract in. So let's talk about A1 times B2 first. We say, well, where are these two values in a 2 by 2? What we're saying is that these are the product of the mains. We say product on the main diagonal. Okay. So we'd say that A2B1 now, if we were to say A2B1, this is the product of the opposing. So this right here is the product of the opposing diagonal. But essentially, when you do this, when you say the product of the main minus the product of the opposing, you get some real number. You get a scalar, okay? So the scalar value associated with these 2 by 2s, we're just going to find the determinants down here and see what we come up with, and then maybe do a little bit of commentary on this. But the first thing I want to do is this. I want to find the determinant of A. We're going to write it thusly, and we say the determinant of A can be expressed this way: vertical bars, 2, -1, 3, and 5, and what we end up with here is this. We'd say, well, then this would be equal to 2 times 5. So I'll actually write out my work on this one. We say 2 times 5 minus now, looks like we get 3 times -1. So 3 times -1. So showing my work, I get 10, looks like -3 times a -1 is a positive 3, so I get 13. So we would just literally write this. We say determinant of A, which is equal to this, blocked off matrix here, which is equal to the determinant of A this way, we could write a lot of different ways, is equal to 13. Okay, so the scalar value that's associated with this particular 2 by 2 square matrix is 13. Okay, so let's try this again. We say, what's the determinant of B? We'll do this a little bit quicker, more quickly. Actually, we could just do it now. We could say, instead of rewriting it 5 million ways, we'd say that this would be equal to 5 times 1, or 5, minus -4 times 0, which is 0. In other words, we get the determinant of B to come out to be 5. So that was a lot quicker than last time. And last but not least, we say, looking at this right here, as a matter of fact, this would correspond to either an inconsistent or a consistent dependent system if one thinks about it. But we say, what's the determinant of C? The interesting thing here is we would get 3 times 2, which is a 6, minus now -3 times -2, which is also itself 6, we get 0. So a very important thing we want to make sure we list here is this. This is referred to as a singular matrix. And I make a little note here in the bottom right corner. It says the determinant can be positive, negative, or 0. This is what we could say about it. But also, I guess I didn't make a note of this down here. We say determinant of 0. This is the definition of a singular matrix. So singular matrices we are going to find are often caused by, when you're solving systems at least, like inconsistent systems or consistent dependent systems where you have infinitely many solutions. When we say a determinant of 0 means that we have a singular matrix. So other things, we say yes, a determinant can be a positive number, a negative number, 0. If it's a scalar and a real number, then that makes sense. And then last but not least, we say the determinant of a matrix of order 1 by 1 is defined simply as the entry in that matrix. So that is, if we had a matrix A, and I'm saying matrix A here is just a 1 by 1, and its first row, first column entry is a 3, then we would say that the determinant of A, which could be written this way also, which could be written this way also, would just be equal to 3. Okay, cheers.